Modern Atomic Theory, Quantum Model of the Atom, as translated from Mr. Salter's lecture. Essential questions. What is Heisenberg's uncertainty principle? How do electrons behave according to the quantum model of the atom? What are atomic orbitals? Be sure to copy down everything written on this slide. Louis de Broglie was a French scientist interested in atomic science. Broglie used Einstein's principle of light-particle-wave duality, which stated that light is both a particle and a wave, to come up with a wave-particle theory that applied to other particles. This theory states that all matter of the universe consists of particles which also have a wave-like nature, which means that everything from you to your furniture is made up of particles which have some wave-like properties. He also stated that larger particles have a less wave-like nature, while smaller particles will have greater wave-like natures. He then stated that electrons behave like standing waves. And if the electron behaves like a standing wave, that means there will be certain places in the atom where the electron cannot be. This is due to constructive interference, which is where the waves cancel out. So, at certain places in the atom, the wave-natured electrons will cancel out and cannot exist there. Because we understand that electrons have wave-like properties, we can understand something called the Heisenberg uncertainty principle. This principle states that because the electron is a wave, we cannot know where it is at any given moment and know its momentum. Note, for this class, rather than the momentum, we will be looking at the energy. So, if we know the exact amount of energy an electron has at any given moment in time, we cannot know its exact location inside the atom. That is very important to understand. The best we can hope for is to have a probable location. If we know the energy, the best we can do is find where it might be, and vice versa. If we know the location, we won't be able to know the exact energy. It's more important for us to know the exact energy than location in this class. Now, the reason we cannot find the exact location of an atom is because if we have the atom's energy and we try to find the electron, the simple act of finding the electron will alter its location. Now, although these points are in your notes, they are very important, so make sure you know and understand them. Electrons are negatively charged subatomic particles that have wave-like properties. It is impossible to know the location and velocity of an electron at the same time. If the velocity of an electron is known, then the energy of the electron is known by the equation E equals 1/2 mv squared. If the velocity of an electron is known, then only the probability of where an electron can be found in the atom can be determined. Now we can begin looking at the fundamentals of our current model of the atom. All of these fundamentals are based off of complicated math, but we will only be looking at the solutions to those equations. Now, these first 2 points have already been learned by us, but make sure you understand them before we move on. Electrons cannot exist just anywhere with respect to the nucleus. They can only be found at certain discrete, specific distances from the nucleus, which distance may be calculated using quantum mechanics. These distances correspond to energies. The further an electron is from the nucleus, the greater the potential energy. Now, Schrödinger developed the mathematical equations needed to find the probable location of an electron inside an atom. The solutions to these equations are called wave functions, and are simply the probable regions where an electron will occur with a certain amount of fixed or quantized energy. Now, here are 2 pictures of wave functions. You can also look at pages 4 and 5 of your packet for other examples. The one on the left is an example of an s orbital. The one on the right is an example of a p orbital. For both wave functions, each dot is the probable location of where an electron could occur. Where the dots are heaviest at is where the electrons are most likely to be found. Now, note that these are both 3-dimensional shapes, which we call electron clouds or atomic orbitals. There are more than just s and p orbitals, though. There are 7 different types of orbitals in all: s, p, d, f, g, h, and I, and they can also be called subshells. The first 4 are the primary orbitals, but we will not be talking about F today. Now, within a shell, not all of the subshells are at exactly the same distance from the nucleus, and so they have different energies. The s subshells are at the lowest energy, followed in order by p, d, f, g, h, and I. There are 3 individual types of p orbital, which can be seen on the next slide. These are px, py, and pz. They are named for which axis they are arranged along. You will need to know how to draw the s and p orbitals. The next type is the d orbital, of which there are 5, but you don't need to know how to draw them. Now, it is important to note that these shapes don't actually exist inside the atom. They are merely solutions to mathematical equations. This is a diagram of the s, p, and d orbitals. You will need to know how to draw the s and p orbitals and that there are 5 d orbitals. Note that in this example, the p orbitals have been labeled with numbers. For our class, we label them px, pz, and py. For those are the axes the orbitals lie across for each respective orbital. This is the end of this lecture, so make sure you go back if you don't understand something. Also be sure you can answer the essential questions from the beginning of the show.